Hello everyone, my name is Michal Kopec and I am a junior embedded C developer at FreeMDEP. I am interested in Coreboot, Linux and open source software in general, and this helped me get a job at FreeMDEP where I work with Coreboot on laptops and network appliances. A little bit about who we are. We are Coreboot license service providers since 2016 and leadership participants, UEFI adopters since 2018, Yocto participants and embedded Linux experts since 2019, official consultants for the Linux Foundation FWPD/LVFS project since 2020, and IBM Open Power Foundation member since 2020. In this presentation, we'll be discussing the status of Coreboot on recent Intel platforms. We'll explore why you might want to have Coreboot, what kind of blobs are necessary, and how we can provide the same features that proprietary firmware from an ABV can. We'll also touch on the biggest problems we encountered while porting Coreboot for a new laptop for our customer. So currently, most mobile SoCs made by Intel are well supported in Coreboot by Intel and Google, with a lot of support being developed before the chips themselves are actually released, and open source firmware vendors and the community fill in the gaps where needed. Intel publishes FSP binaries for several popular mobile architectures, ranging from Skylake to Tiger Lake, and this makes for a good starting point for porting Coreboot to other recent laptops. Thanks to Google's Chromebook line of laptops, Coreboot is one of the most popular firmware solutions on the market. Some Linux-friendly laptops like System76, Purism, and Starlabs have also started to use Coreboot for their products. Looking at the success of the products and the popularity of older ThinkPads supported by Coreboot, we can see that Coreboot is very desirable among open source fans and the privacy-conscious crowd. While Coreboot on x86 requires a number of blobs for initialization for a lot of hardware, I think there are still a lot of benefits for using Coreboot instead of proprietary firmware from an IBV. So first of all, code other than the blobs can still be audited and modified for the user's needs. It has a smaller attack surface compared to most proprietary solutions. For example, it tries to do as little as possible in SMM, system management mode. It's faster and more lightweight. It's more flexible, can run a number of different payloads and be customized in ways proprietary firmware can't. And support cost is lower thanks to the community, especially after the official support ends. Our customer sells laptops based on Clevo designs. They came to us asking for a replacement for proprietary firmware that the laptop came with. Their focus was on improving the user experience and security of their devices. The laptop is based on an Intel Tiger Lake SoC, comes with an embedded controller running proprietary firmware and optionally with NVIDIA hybrid graphics. The goal is to replace the original UEFI with Coreboot while retaining full functionality of the device. Recent Intel platforms need a number of blobs to boot properly. FSP is used for memory and a large part of silicon in it. The ME blob is also required and takes care of some power management functions. For example, we found that in the recent Intel chips, the ME blob can be disabled using tools like ME Cleaner, because then sleep mode wouldn't work properly, and that's required for a laptop. And at the moment, the only option for graphics in most recent chips is the proprietary GOP driver included with FSP, so there's no libgfx in its support yet. The embedded controller is an ITE IT5570E running proprietary firmware. There is some support for it in Coreboot, but it's mostly specific to other versions of firmware. This means we couldn't reuse a lot of the ACPI code that already exists. The datasheets are not publicly available and the proprietary firmware interface is not well understood. Our work was thus mostly based on reverse engineering and poking at the EC memory. This increases porting complexity and is the major reason why porting Coreboot to laptops is difficult. Some of the hotkeys were particularly challenging, and everything came down to comparing ECRAM contents between Coreboot and original firmware and just flipping bits until the keys started working. On Intel platforms, we can use the Intel HID event filter to handle some extra hotkeys without a special OS driver. This helped us to handle almost all hotkeys and firmware without needing a driver. For the payload, we chose Tiano Core as it gives us the ability to boot recent operating systems. We're using a customized Tiano Core payload with some extra features such as secure boot, iPXE for network booting, and support for self-encrypting drives. And eventually, we plan to upstream the changes to coreboot.org. So hybrid graphics. Many new laptops come with a hybrid graphics setup where we have an integrated graphics card handling most daily duties and a second powerful GPU that only comes online when it's needed. So for example, when someone's playing a game, then it needs to be turned on. And when it's no longer used, it can be shut off for power savings. NVIDIA's version of this is called NVIDIA Optimus, and no documentation for Optimus has been made publicly available. So a lot of development is based on reverse engineering and just trial and error. We found some attempts at supporting Optimus in Coreboot, but they wouldn't work well for one reason or another. The biggest problem was the drivers not being generic enough to support many different configurations that we want to support. So for example, our laptop has the GPU connected to the PCH root port, and none of the existing implementations know how to deal with that. Another problem is NVIDIA not being consistent with their ACPI interface for power management. So, for example, there are at least 3 different methods to turn a GPU off that have been found in laptops in the wild. We found that the Intel RTD3 driver present in Coreboot at the moment would work well for Optimus and Linux, but Windows would, for example, refuse to load the driver, the NVIDIA proprietary driver, or it would refuse to shut the GPU off. The problem was that the Windows driver expects a subsystem ID to be set, and the GPU forgets the ID every time it's turned off. This meant that we had to add code to set the subsystem ID after each power cycle. So in the end, we developed a new Optimus driver for Coreboot that creates ACPI code to power manage the GPU and deals with any NVIDIA-specific quirks. And we think it's generic enough that it should work on other Optimus laptops with Tiger-like CPUs, and we hope to upstream it when it reaches good enough quality. There are also other features such as GC6 power state, which allows the GPU to save more power while it's powered on. So kind of like CPU C states. They are also handled entirely in ACPI, but there's no public documentation for it at all. And as far as we can tell, it requires an entire ACPI stack of methods for the driver to make use of it. And eventually we want to support these too, but at the moment we do not have this implemented. As for the security, we found that we can have a reasonably secure firmware while still respecting user freedom. So the user still has the ability to flush their own firmware using an external programmer if they wanted to. But for regular users, vboot protects them against unsigned binaries being flushed from the OS. We also implemented Secure Boot with the ability for the user to enroll their own keys and remove the default keys completely. As for Windows compatibility, we had some difficulty implementing it correctly. So Windows compatibility is perhaps not crucial for most Coreboot developers. And we think that it's required for Coreboot to reach mainstream adoption to have good support for Windows booting. So we need to treat both Linux and Windows as first-class citizens. And some of the problems we found were the ACPI errors on Windows. So Windows has a very strict ACPI interpreter. Some errors are ignored completely by Linux, but will cause Windows to blue screen at boot time. Backlight. We found that the backlight would work perfectly on Linux out of the box, but Windows needs a complete functional ACPI backlight implementation, else the brightness keys wouldn't work at all, or the backlight would be powered off completely. Windows Update. We found that the SMBIOS vendor fields would need to match perfectly with vendor firmware, as the Windows Update would refuse to find any drivers. So hybrid graphics, I've already touched on that. We found that the Coreboot RTD3 driver would work fine on Optimus, but on Linux, but would review special quirks for Windows. And none of these are really easily debuggable and requires just lots of trial and error. And in the end, we did manage to install and boot Windows 11, as you can see at this screenshot below. Another large problem for us was getting S0IX suspend to work correctly. Since the Tiger Lake and newer Intel SoCs, traditional S3 is no longer supported. So S0IX, or modern standby, requires all components to enter lower power states, and we spend a long time figuring out which device is preventing the laptop from entering deep sleep. VEC also requires special care to enter sleep mode. In the future, we want to help deliver many more free as possible laptops to the market to a wider group of users, and we believe using Coreboot can deliver a better experience than proprietary firmware solutions from an IBV. Eventually, we want to upstream as much as possible of what we've developed during this project. We also want to work to bring more advanced security features such as DRTN to more users. And that's it.